Wave parameters. I'm going to start off this lecture with a discussion of fundamental versus intuitive parameters. And this is a framework that I like to put this in to sort of categorize all of these different parameters that we talk about in electromagnetics, like permeability, permittivity, refractive index, impedance. Where do they all fall? What's the sense and reason behind this? Then we're going to take a methodical step-by-step approach through these and get a physical feel of what all these things mean, what they mean, and how they're related. So let's go ahead and dive into this. By fundamental parameters, I am talking about the material parameters that appear in Maxwell's equations. Specifically, it's the permeability, the permittivity, and the conductivity. So those are very fundamental to Maxwell's equations. And in fact, if we want to solve anything electromagnetically, these are the parameters that we need. The problem with them is that they're not very intuitive. I can't look at the permittivity and permeability and say anything about the wave. I don't know what its amplitude will be. I don't know how fast it's going to travel, the relation between E and H, or anything about the wave itself. So they're not very intuitive to interpret anything physical about a wave. They're just fundamental to Maxwell's equations. So instead, there's a whole list of parameters that give us very specific information that has physical meaning. And we need to understand how to calculate these intuitive parameters from the fundamental parameters. But make no mistake, these intuitive parameters, they are not fundamental to Maxwell's equations. They're just numbers that have physical meaning. So let's go ahead and start stepping through these. We start with the historical wave equation. And someday when I have time, I'd like to sit down and really investigate the history of the wave equation. I do know that the wave equation has been known since at least the 1700s. And this is the basic form that it was known in. And this psi parameter is just the wave disturbance. If you're wiggling a rope, it would be the height of the rope. An electromagnetic wave, that would be the electric field. If it's a sound wave, it's pressure in air. So it's just whatever kind of disturbance it is, all waves fall into this same equation. And they have to because it's the wave equation. And so what was known is if you could write this, here is the frequency and the velocity of the wave. So that's been known for hundreds of years. Now along comes Maxwell, who fixes Faraday's equations, really, fixes them, adds the displacement term, and is able to derive the wave equation for the first time, the electromagnetic wave equation. So that was derived, and so then Maxwell compared the electromagnetic wave equation to the historical wave equation and realized that this omega squared mu epsilon term, that has to be the frequency divided by velocity squared. So based on that, Maxwell set those equal and for the first time was able to derive the velocity of an electromagnetic wave from the electrical parameters, the permeability and the permittivity, and that was extremely cool. So that's our equation for the velocity of a wave in a medium described by a permeability and a permittivity. So here's our equation. What about if we are in a vacuum? So in a vacuum, our permeability is just the free space permeability, and our permittivity is just the free space permittivity. So we can go ahead and fill those into our velocity equation. And now we're talking about the speed of light. When people say the speed of light, they're referring to a very special case where light is in a vacuum. Well, in reality, light changes speed when it goes from vacuum into water or glass or other mediums where it actually travels slower. So in some ways, this is a bad title because the speed of light changes. But the speed of light is referring to the special case of light or any electromagnetic wave in a vacuum. So we give that a special symbol. We give it a C0, and it's equal to 1 over the square root of the product of the free space permeability times the free space permittivity. And here is the speed of light. And in fact, that is exact. There are no decimals. The reason that is exact is because that's how we define 1 second. We define that based on the speed of light in a vacuum. Another thing that I do is I put this little not term here. In some papers, you will see just C alone. And sometimes that means the speed that can change, just the speed in the different medium. The C with a not subscript always refers to the speed of light in vacuum. In yet other papers, I see C, which does mean the speed of light in vacuum. So C alone is rather ambiguous. And when I see that in an equation, I won't immediately know what they're talking about. I'll have to read and get the context to figure out what they mean by C. So to avoid that ambiguity in everything I do, I always do the C naught. So if you ever see me use just C alone, I'm probably talking about the velocity that can change depending what medium it's in, but I really avoid doing that. So here's our expression again for velocity. We know that the permeability can be written as the product of the free space permeability times the relative permeability, and the permittivity can be written as the free space permittivity times the relative permittivity. So let's put those expressions in our equation for velocity. So we've replaced the permeability with this product, and we've replaced the permittivity with this product. The next thing I want to do is group these two free space terms together and the two relative terms together. And we also separate the square root. Now we can recognize already that this first term is the speed of light in vacuum. That must mean this term, whatever this is the term that describes how much the wave slows down when it enters a medium that's not a vacuum. So this is what refractive index is. It's the factor by which a wave slows down inside of a medium. And so we define it as the square root of the relative permeability times the relative permittivity. Don't mistake these terms here for the permeability and permittivity. Those are the relative permeability and relative permittivity. So don't make that mistake. So that's refractive index, the factor by which a wave slows down relative to the speed of light in vacuum. So the fastest light can ever travel that we know of today is in a vacuum. In anything else, it slows down. So refractive index, its very smallest value is 1. It only gets bigger from there. So finally, we can write the velocity as the speed of light in vacuum divided by refractive index. Here we're looking at a wave traveling at something with a refractive index of 1, so it looks like we have a vacuum on the left, and the wave enters a second medium which has a refractive index of 3. That means the wave on the right is traveling at 1/3 the speed of the wave on the left. One thing we notice, and we're tracking with these green dots and the bar, is that the wave is oscillating at the same frequency. So in a linear medium, and also media that's not moving, and the media is not moving here, just the wave, frequency is constant. So that's the thing that's fixed that doesn't change. However, we can see that the speed changes, and also because the speed is changing, so is the wavelength. So we can write velocity as the speed of light divided by refractive index, and we can certainly see that that changes on both sides because the refractive index is different. And the wavelength also changes. So we have the wavelength without a subscript. This means the wavelength that can change. The higher the refractive index, the smaller that is. And so it's the free space wavelength with never changes, that's a constant, divided by refractive index. Just like the speed of light symbol, this is especially a symbol to be cautious of in the literature. When you see lambda alone, sometimes they mean the free space wavelength, other times they mean the wavelength that just happens to be whatever it is inside the medium, the one that can change. And so that's ambiguous, that's confusing. When I see lambda alone, I know that I have to read further and deeper to try to figure out what they mean by lambda alone. So to avoid the ambiguity, I almost always use this lambda not. But when you see me use lambda alone, I'm talking about whatever the wavelength happens to be inside the medium we're analyzing. But I don't like adding that extra level of confusion, and almost without exception, I will always use the free space wavelength divided by refractive index instead of just lambda. But you will see it once in a while. So frequency is constant, speed and wavelength change in proportion to this refractive index. Now speed, frequency, and wavelength are related, and this is for any wave. So the speed of a wave is frequency times its wavelength. Now in a vacuum, that velocity is the speed of light. So the speed of light equals frequency times the free space wavelength. So now we have really two equations for velocity. Velocity is related to the permeability and permittivity. We can also calculate it from frequency and wavelength. Well, this gives us an opportunity now to solve this equation for wavelength. So we can get these crazy expressions to calculate wavelength if we know the frequency and the material properties. Now on to the wave number. Remember, we first identified and defined the wave number when we derived the wave equation, and we saw this omega squared times mu epsilon, and we called that k squared. So that means our definition for k is really omega times the square root of mu epsilon. So we replace now the mu with mu naught times mu r, and the epsilon with epsilon naught times epsilon r. And then like we did before, we'll isolate the free space terms and we'll isolate the relative terms. We can recognize that this is 1 divided by the speed of light, and we can recognize that that is a refractive index. So our wave number is the angular frequency divided by the speed of light times refractive index. That's one very useful definition. Let's dig deeper. The angular frequency is related to the ordinary frequency through omega equals 2 pi f. Frequency, if you remember, is speed of light divided by the free space wavelength. The free space wavelength is refractive index times wavelength. This is the wavelength that changes, the form that I rarely use, but make no mistake, that's the wavelength that can change depending what medium we're in. So borrowing this equation we have up here, I'm rewriting that omega 1 over speed of light times n, but now we have an expression to replace omega with. So we go ahead and take this expression and replace omega, and now we see that we have the C naughts cancel, these two n's cancel, and we end up with 2 pi over wavelength. And this actually is a huge conclusion about the wave number. It is 2 pi divided by wavelength, and the wavelength happens to be whatever the wavelength is in the medium. That's the wavelength that can change dependent on refractive index. So wave number, 2 pi over lambda. That's an important one. So this wave number actually can also be a vector. We can have a wave number in the x, y, and z directions, and when we lump it together, we call that a wave vector. A wave vector points in the direction the wave is going. We mentioned that in the last lecture, but didn't go into too much detail. So here, to the best of my ability, is how I visualize the wave vector. And you can see the wave, it's the orange, white, and green planes, and they're propagating in a particular direction. And that direction's changing, but that k vector is always perpendicular to those planes of the wave. We can also see the wavelength. The magnitude of our wave vector is still 2 pi over lambda, very consistent with what we talked about on the last slide. I happen to also be visualizing this along with the electric and magnetic fields. And so the electric and magnetic fields, they're perpendicular to each other. They're also perpendicular to K. So in the end, the wave vector is conveying two pieces of information. The magnitude is conveying wavelength, and the direction is talking about the direction that phase is marching in a wave, the direction of the wave. Back to this picture again of a wave entering into a medium. And if we know the wave vector in each of these media, then from the magnitude we could calculate the wavelength, because the magnitude of the wave vector conveys wavelength. This isn't such a hard concept. Now this one may be a little weird if you're new to this, but when the frequency is known, that means the free space wavelength is known. And in this case, it turns out we can get refractive index from the magnitude of the wave vector. And this is a very common way that I think. Now, why is this? Okay, so the magnitude of K is 2 pi over lambda. So instead of saying lambda, we're going to put this in terms of lambda naught, but we have to divide this lambda naught by n1, so that really we just have a lambda down here. But at this point, we have a 2 pi over lambda naught. That would be the magnitude of our wave vector in free space, or the magnitude of the wave vector in a vacuum. We write that as K naught. And in fact, this is a big definition. Anytime we have K naught, we call that the wave number, and it is the wave number for vacuum, 2 pi over the free space wavelength. So this is a constant. And by the way, because it's 1 over wavelength, this is kind of a frequency term, and you'll hear that a lot, that the wave number is frequency. Well, it's not exactly frequency, but being 1 over the wavelength, it has the same interpretation as frequency. So anyway, this is K naught, and now K naught's a constant, but 2 pi over lambda is K naught times refractive index. So when frequency is known, that means this wavelength is known, and K naught's a constant. The magnitude now of the wave vector conveys refractive index. Of course, it's multiplied by a constant, but in terms of the information it's conveying, that's not necessarily important. So the magnitude of the wave vector changes on both sides, and since we know the frequency and that's constant, the magnitude of the wave vector on both sides of these interfaces conveys refractive index on both sides of the interface. I know this is sort of confusing, but the more practice with these wave vectors we get, the better. The easier this will come. Now, if we don't know frequency, we can't conclude anything about refractive index. We got to go back to the previous slide, and all we can conclude is that the magnitude of the wave vector conveys wavelength. Now let's talk about the material impedance. I like to describe the impedance as relating the balance between the electric and magnetic fields. They both exist with a different amplitude, different phase, and the impedance describes that balance. So think of it this way. Let's say we have a medium, and we excite it with an oscillating electric field, and it's oscillating with some amplitude and some phase. That medium then responds with a magnetic field that potentially has a different amplitude and a different phase than the electric field. And so we call that the impedance that relates the two. But in the simplest form, it just is a balance between the electric and magnetic fields. So if we want to derive an expression for this, we will go back to our expressions for the plane waves, determine the amplitudes of these quantities, divide them, and then we'll have an expression for the impedance. Well, the amplitude for the electric field is rather easy. The amplitude for the magnetic field is not so easy, so let's look a little bit deeper into that. So to isolate the amplitude of the magnetic field, I like to do two things. First, I will come up with a normalized wave vector. So this is in the same direction as the wave vector, but has a unit amplitude. And then we have the scalar wave number, which conveys the magnitude of the wave vector. So these two together is the wave vector. Then over here, where we had our polarization vector, I'm going to write that as a normalized polarization vector. So it's in the same direction as the polarization. However, it has unit amplitude. And so the magnitude is actually conveyed by E naught over here. So together, this is the polarization vector. And why we're doing this will make some sense in a little bit. So I can pull K and E naught to the outside. And what I'm left here is just the normalized K cross product with the normalized P. And since these two are 90 degrees with respect to each other, the cross product still has an amplitude of 1. And so that means this is the amplitude of H. And so that's why we factored out those terms. This was our big conclusion from the last slide. And now finally we can write the amplitude of the H field. Now we know the amplitude of the electric field and the magnetic field with much simpler equations. We're now ready to figure out what the impedance is, the expression for impedance. So here's our definition. It's the amplitude of the electric field divided by the amplitude of the magnetic field. Well, the amplitude of the electric field is just E naught. We started with that. However, the amplitude of the magnetic field is now E naught times K divided by omega mu. Well, these E naughts cancel, and we're left with omega mu over K. And that's kind of weird, and we can do some more manipulation and simplify that. Remember that our wave number was omega times the square root of mu epsilon. This is what we extracted from the original wave equation. So this gives us an expression to replace K down here. When we do that, our omegas cancel. We also have two mu's that combine, and in fact, just comes to the numerator. And in the end, we have impedance is the square root of permeability divided by permittivity. Now that we're armed with this concept of impedance, one of the things I like to do is write the expression for the magnetic field in terms of the impedance. It seems to give me a little bit better physical feel of what's happening. So our magnetic field is now the cross product of the normalized K with the polarization vector. This is not the normalized polarization vector, and we're not normalizing this because we need the information from the amplitude of the electric field. So that comes in through this polarization vector. But the normalized K vector cross the polarization vector tells us the direction that the magnetic field is oscillating in, plus part of the information for the amplitude. The rest of the information comes when we divide by impedance. So it's really the polarization vector divided by impedance, the magnitude of that, which is the amplitude of the magnetic field. And of course, it has the same complex exponential. So just to remind us, the impedance was defined as the amplitude of the electric field divided by the magnetic field, which is why I like to describe impedance as the balance between E and H. And we found that that's the square root of the permeability divided by permittivity. Now in free space, we have the free space impedance, which is the square root of mu naught over epsilon naught, and that is equal to 376.73 and a bunch of other decimal ohms. So the impedance of free space is almost 400 ohms. That means the electric and magnetic fields are about 3 orders of magnitude different. And this actually has some consequences, the fact that they're different. When we get to simulations and computations, when we're doing math with numbers that are orders of magnitude different, that's usually bad practice, and we have to do some wizardry to fix that. But for us in this class, that makes no difference. It's just interesting to note that E and H are about 3 orders of magnitude different. So that's it for this lecture.